Hello students, and welcome back to my Hanson Math YouTube channel. This lesson today is a big one. We're discovering the derivative, taking our first steps, wading into the water of calculus. So in this investigation, we'll look at secant lines, tangent lines, limits, and finally the derivative. So if you've heard of the derivative before, maybe it sounds a little bit scary or off-putting, don't let it be that way. I'm going to break down for you exactly where this formula comes from and briefly what it is used for, what it finds. Calculus is a Latin word literally meaning small pebble. So remember this next time you're at the dentist in the chair and scrape, scrape, scrape on your teeth, the dentist or hygienist is removing calculus. Yep, that's the nasty buildup on your teeth. The medical word is calculus. Small stones, small little pebbles. In the 17th century, Isaac Newton and Gottfried Leibniz developed what became known as calculus. These men developed the idea of a line tangent to a curve. So we too shall explore this idea of a line tangent to a curve in this video in the coming moments. So speaking of a curve, here we have a hypothetical space shuttle launch, and we have time in seconds on the horizontal x-axis and distance in meters on the vertical axis. So, as an example, this start point here would be that after 60 seconds after launch, the space shuttle is approximately 5,000 meters in the air. So this is pretty bread and butter stuff here. But it's only natural, since we're comparing distance versus time, that we can measure this, the speed of the space shuttle in meters per second. Now, there's several ways to do this. Okay, one way to do this is with this line here that connects point A to point B. So we're going from approximately 80 seconds into the space shuttle's flight path to 120 seconds, and this line will tell us something if we know how to read the graph. So I'm going to ask you folks in YouTube land, what name in geometry do we give this line AB? Time's up. It's called a secant line. So the secant line intersects this red curve twice, here and here. And what I like to point out to folks is with the secant line, you always have some area between the secant line and the curve that it intersects, like so, okay? So with that in mind, let's talk about how we can use this secant line to find speed. The secant line A to B represents the average rate of change from A to B, or average speed, in this case, meters per second. Now, I just want to make it abundantly clear that while A to B is linear, the path of the space shuttle is not. And you can see that the curve here, when you start, is kind of gradual, and then it gets steeper and steeper, so the speed is increasing. And again, this is just a snapshot of the graph. We only go out here to about 140 seconds, which is just over 2 minutes. So at some point, this curve is going to change. This is just a little window into the space shuttle's flight path. But I just wanted to point out that while this secant line is linear, the actual speed of the rocket is not. Okay, that's very important to note. So this begs the question, how can we measure the average rate of change that would be given by the secant line that we're going to call AB? Well, it's just the slope of the secant line A to B. So if we can find the rise over run from point A to point B, we can look at the average rate of speed of the space shuttle during that time interval from 80 seconds to 120 seconds. So if we think of 80 seconds as the first time we're measuring, and 10,000 meters as the first height we're measuring, and 120 seconds as the second time we're measuring, and 50,000 meters as the second height we're measuring, we can do rise over run, which is change in y over change in x. And little m is slope. So our second y is 50,000 meters minus our first y is 10,000 meters. Okay, that was our change in height, vertical. And our change in horizontal or time would be gotten by 120 seconds minus 80 seconds. Okay, so if we simplify this a little bit, 50,000 minus 10,000 is 40,000 over 120 minus 80 is 40. Now, if we simplify this a little bit, we can divide by 10, which will knock out a 0 and a 0. So we're left with 4,000 divided by 4, which is just 1,000. And if we're paying attention, our y stuff, our rise was in meters, and our run was in seconds. So from the 82nd point in the flight to 2 minutes, the space shuttle was going at approximately 1,000 meters per second average speed. So keep in mind that, again, this speed of 1,000 meters per second is just an average speed over this 40-second time interval. Just like think of you running for 40 seconds. You're going to probably speed up or slow down a bit, but it can be helpful to think of your average or typical speed over that time window. But that begs the question, what about a specific or instantaneous speed at a point in time? Say exactly at 80 seconds. So if we think about the rocket taking off, okay, it takes off and it's speeding up. And then what if we want to know right here at point A, 80 seconds into its trip, what was its speed exactly at that moment? Because it might never have that speed again because it's changing, okay? It's not linear, it's changing. What was the speed exactly precisely at the 80-second mark? We can do that, so let's see how limits factor into all this. Recall from our work with limits that we think of specific x values we're approaching. So for example, as the limit x approaches some value c, we're also approaching a y value given by f of c. So all I'm saying here is along this red curve, as we're moving in from the left, and then we can move in from the right, we're approaching a particular height, and we can call that height f of c. That's the height is the function value we're approaching, okay, as we consider the limit. X approaches some value. So if we are thinking of c as our input and f of c as our output, we could rename our starting point A as c comma f of c. However, that's a little bit cumbersome, so we're just going to make it a little bit easier and more consistent to understand. For the sake of familiarity, we're just going to call this point x comma f of x, which again, that should be pretty bread and butter stuff for you. This point A could just be called, xy, f of x is the same as y. So this point here, point A, we're just going to choose to call it x comma f of x. But we want to eventually get to point B up here. So how we're going to do that is we're going to take the position of this point here, and we're going to add a value or a change called delta x to the x coordinate. Now, delta x, this triangle, delta means change. So change in x means we're going to add to the x value. So adding is going to move us to the right. And then if you move to the right, you also have to move up to hit the function again, which will take us to point B, okay? So we're going to add some value of x that we're calling delta x. Thus, point B, where the secant line intersects the curve for the second time, can be represented as x plus delta x, comma, f of x plus delta x. Now, this all looks very confusing, but all it's saying is the following. If we take the coordinates of point A here, which are called x and f of x, which is like y, right? And we add an increment to it that we call delta x, we add that to the x and we evaluate that into the y, that's going to move you so far over and so far up to point B. This is just a way to mathematically express it, okay? So instead of saying A and B, we can call point A x comma f of x, which is like xy, and we can call point B x plus delta x comma f of x plus delta x. Again, this delta x is just a certain amount of change to move us over and then up. Okay, I hope that makes sense because this is fundamental to the development of where we're heading. So since rate of change, which can also be called speed, which can also be called slope, is just rise over run or vertical change over horizontal change, the slope of the secant line can be represented by this f of x plus delta x minus f of x all over delta x. Now, this might look pretty terrifying, but let me try to break it down here. So notice that you have the height of this point here, which we originally called point B. The height is given by the y-coordinate, okay? The height of this original point A is given by this y-coordinate. If you subtract the y-coordinates, if you subtract the position of height, you literally get this change right here that I'm putting in blue. So if you take this, which you could think of as your y2, f of x plus delta x, that's right here, and you subtract your original height, which is f of x, that's right there. So all this numerator is here is just the change in height. It's the second height, f of x plus delta x, subtracted with the original height, f of x, which is like y. Okay, so that's your rise or your change in y. And then we're dividing by your run or your change in x, and we're saying the change of x is just this right here. It's some arbitrary change in time. So that's your formula. It's just a kind of a messy looking version of slope. It's just rise over run using different symbols and terms. So if this slope can be given by this expression, and it gives us the slope of the secant line, which is the average rate of change between the 2 points, what happens is we take the change in x called delta x. What if we shrink it smaller and smaller? That is, we make delta x approach 0. Making delta x approach 0 means there's really no distance between these 2 points, as you'll see. So let's take a look at what happens when we shrink delta x down to 0. Here you'll see that I made this distance here, delta x, I made it a little bit smaller. You can see these 2 points got closer together and there's less space between the secant line and the curve. Now I made delta x even smaller. These 2 points got closer together and there's even less space between the secant line and the curve. Now I made delta x even smaller. There's less distance between these 2 points, and there's hardly any space between the secant line and the curve. And then finally, I shrunk down delta x so infinitesimally small, there's practically 0 space between the 2 points. And look what happens now. It's not a secant line. This purple line just barely skims, it just nips or clips the red curve right here. So what is this type of a line called? As delta x approaches 0, the secant line turns into a tangent line. So now we have a tangent line to the curve, which does not mean the average rate of change, it means something else. The tangent line will give us the slope or speed of the space shuttle at a particular instant or a particular point in time or particular x value. So it's not an average rate of speed at all. It's an instantaneous snapshot of the speed at a very particular moment in time. If the previous example was a little bit confusing to you, let's try to look at this from a different perspective. So let's look at a very familiar function, f of x equals x squared plus 1, which is the parabolic curve here to the right. And suppose we think about this as we have time on the x-axis and distance again on the y-axis. So we could be looking at distance over time, which is speed. So what if we were thinking about this red curve modeling the speed of an object, and what would be the exact speed of an object at 2 seconds into its trip? So if we go over to 2 and up to 5, we're looking right here on the graph. And now we should be trying to clearly establish if we want the rate of change or the speed right there, we'd have to be looking at the slope of the tangent line to that point right there, okay, something like that. So let's zoom in on this picture a little bit and see what we can figure out. So we now know that this is our new expression for rate of change or slope or speed, f of x plus delta x minus f of x over delta x. And remember, this is just something new to you. It's just a different way to express slope or rise over run or change in y over change in x. Okay, they're all equivalent expressions. So if I were to try to find the line tangent to this point, see, I zoomed in. This is just a small snippet of that parabola from the previous screen. And I'm trying to look at what the slope would be to the curve at the point 2 comma 5. Now, delta x here, this change in x, it would shrink down to 0. So we'd be looking at the slope of the tangent line right at this point. But if I literally substitute in 0 for delta x, I'm going to get division by 0, which is undefined. So let's try this from a different perspective. So what if we, instead of shrinking delta x to 0, which we can't do analytically, what if I choose a very, very small delta x of 0.01? So that would mean that we really, instead of 1 point that you see here, there's really 2 points there, but they're really, really close to each other, so much so that I can't even plot it. So let's have delta x be 0.01. We've got our point 2 comma 5, which we're trying to find the speed of the object at x equals 2. And if we add a 0.01 as our delta x, that bumps the next x coordinate as 2.01. And if you evaluate that, you get out for the y value 5.04. So let's start breaking this down a little bit using our new slope formula. So we have our function, and this here says we're going to plug in x plus delta x. So our function is x squared plus 1. So we have x squared plus 1. But into the x, I'm going to plug in 2 plus the delta x, which was 0.01. Okay? So here is the value 2 that we're looking at the speed at x equals 2. I'm adding in this small little delta x 0.01. I have to square that because we're looking at x squared, and then plus 1 was also part of the function. Okay, so that takes care of this. Now I have minus f of x. Okay, so I have minus x squared, and again, we're plugging in 2 for x squared plus 1. Okay, that's the numerator plugging in all the particulars. Okay, x is 2, delta x is 0.01, the function is squared plus 1, that's coming from here, minus the function x squared plus 1, but evaluated at 2, so 2 squared plus 1. Got it? All over delta x, which is this little small change of 0.01. Okay? So now we have 2 plus 0.01 squared, so we're going to evaluate that. 2 2 plus 0.01 squared is 2.01 squared, which is 4.0401 plus this one minus the result of 2 squared plus 1. Well, 2 squared is 4. 4 plus 1 is 5. Okay, all over 0.01. So now let's simplify the numerator. We've got 4.0401 plus 1 minus 5. That gives us 0.0401 all divided by 0.01. So now if you do the final division, again, you'll get an answer because we're not dividing by 0, we're dividing by something very close to 0. 0.0401 divided by 0.01, which is 1/100th, is, drum roll please, 4.01. So using this calculation of slope with a very, very small delta x should get us very, very close to the rate of change or the slope right at x equals 2. So this is our rate of change, which would be, let's give it a unit. It could be meters per second. It could be miles per hour. Okay, so the slope we expect to be very close to 4. In this case, by hand, we got 4.01. But sometimes in life, calculations like this with a little bit of maybe round off error, they're not acceptable. Okay, they would not work in engineering. Things would go very, very badly and very, very wrong. So we're going to move forward here with investigating how do you solve this from an algebraic perspective where you can algebraically, you can let delta x get all the way to 0. And we're going to do that using limits and the algebraic techniques we've already looked at. So hang on to your hats. We're about to do some serious calculus. So this idea of the slope of a tangent line at a given point on a curve is called the derivative. So we're finally there. Now we're going to do some calculus with something called the derivative. So the definition of the derivative of a function, the derivative of the function f at x is given by f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Again, this is just a kind of intimidating looking version of rise over run. This is just slope as I tried to show you in the other slide. Okay, this works provided the limit exists, and this f apostrophe x looking here, this prime, f prime of x is read as f prime of x. So instead of f of x, when you find the derivative, the notation looks like this little apostrophe. It's read f prime of x. Here are some facts that you will eventually know about the derivative. And again, this is a little bit putting the cart before the horse. You don't need to know all these today. This is just a little bit of a heads up. The process of finding a derivative is called differentiation. Other notations for the derivative include dy over dx and y prime. Note, dy over dx is read as the derivative of y with respect to x. So again, it's kind of a rise over run type of deal. So let's finally compute the derivative of a function. We're about to do some actual calculus. How cool is that? So we finally made it to an example here, which I'm going to call example 1. We're going to find the derivative of the function f of x equals x squared plus 1. And then we're going to evaluate the rate of change at the points 2, 5, which we just played around with, and then at -1, 2. And then we're going to confirm those using Desmos. So let's start with part A. How do we find or take the derivative of f of x equals x squared plus 1? Well, first, here is our formula. F prime of x, the derivative, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, again, that's the rise, over delta x, which is the run. So again, this is just slope at a particular point, tangent to that point, which you'll see in a little bit. But let's first do this analytically. So we have f prime of x equals the limit as delta x shrinks to 0. And here we have f of x plus delta x. So let me loop that in yellow. What is f of x plus delta x? Well, that means that you take your function and you literally plug or substitute x plus delta x into it. So what I mean by that is if we take our function x squared plus 1, I have to plug this into it. So I have x plus delta x squared. I'm plugging this expression that I roped in yellow into x. It's getting squared. And I'm still adding plus 1 because that was part of my function. And now I will put it in red. We have to do this part of the numerator. We have to subtract the function. So subtracting the function would be subtracting the function x squared plus 1. Okay? That is our numerator. So again, this here I'm pointing to, this is x squared, plugging in x plus delta x, plus 1 was part of the function, and then we're subtracting the function, which is called x squared plus 1. Now, we need to put this all over delta x. Okay? Now notice, there's no way that we could substitute this right away. If we plugged in 0 right now, we'd have division by 0, which we saw in our previous lessons. So we have to keep going. So we have f prime of x equals the limit as delta x shrinks to 0. Now what we're going to do is we're going to take this x plus delta x, this binomial squared, and we're going to work it out. So squared means you have that grouping times itself. Okay, I'm going to do this very slow. So that's what the squared means. You multiply it out twice. Okay, plus the 1. Now we're here, and this minus is like, it's kind of like having a negative 1, and we're going to distribute it. Negative 1 times x squared is negative or minus x squared. And then the negative 1 times the positive 1 is a minus 1. Okay? So that's the numerator, and then your denominator is just delta x. All right? So I'm going to do another rewrite. I'm taking it hopefully nice and slow. F of x equals the limit as delta x approaches 0 of, now we're going to FOIL this out here. We're going to FOIL this out. So first, x times x is x squared. Outer is x times delta x, which is x delta x. Inside is another delta x times x, which is another x times delta x. And then last, delta x times delta x would be delta x squared. All right? So these 4 terms, this is the first, outer, inner, last, from FOILing out the multiplication of these binomials. Now I'm going to rewrite what's left. I have plus 1 from here, then I have minus x squared, and then I have minus 1. That's our numerator, all over delta x. Okay? So now let's see if we can clean this up a little bit. Notice in your numerator, I have an x squared, and down yonder, I have a minus x squared. Those offset, cancel, cancel. I have a plus 1 and a minus 1. Those cancel, cancel, cancel. So now, if I go up here, where I have some space and do a rewrite, so I have the derivative f prime of x equals the limit as delta x shrinks to 0 of, well, what do I have here? I have a x delta x plus another x delta x. So that's 2 of them. So that's 2 of x delta x. And then I have this term here, this delta x squared, so plus delta x squared all over my delta x. Okay? So now what I'm going to do is do a rewrite. F prime of x equals the limit as delta x approaches 0. Notice here that I have delta x in both terms in the numerator and delta x in the denominator. So what I'm going to do is the following. I'm going to cancel this delta x out with this one in the numerator, and it's going to knock the square down just to the first power. So as you can see here, what am I left with? I'm left with 2x plus delta x. Now I have no denominator, it canceled out. So now I can evaluate, I can replace delta x with 0. So I have 2x plus delta x gets replaced with 0. So I just have 2x, and thus you've done your first calculus problem. The derivative of x squared plus 1 is 2x. What this function will do here is this will give you the rate of change or the slope at any point for this original function, x squared plus 1. Okay? So we're going to try to take a look here at how this will work. How will this new function, I should call it f prime of x equals 2x, how will this give us the rate of change at any point? So I'm going to hit pause to clean up my screen, and we're going to take a look to wrap up this video. Okay, so we just found out that if my function f of x is x squared plus 1, its derivative, f prime of x, is just 2x, okay? So I claim that this function here will give you the slope at any point, all right? The instantaneous rate of change. So let's take a look. So what if I want to figure out what is the slope or the rate of change at the point, this point here, 2 comma 5, which we looked at in the previous slide? Well, what I'll do is I'm going to plug that point into my derivative, f prime of x equals 2x. So since this equation is in terms of x, I have to plug in the x value here, which is the 2. So I have 2 times 2, which is 4. So the original function, x squared plus 1, it should have a slope of 4, or 4 is the slope at the point 2 comma 5. Well, do you believe it? Is that hard to believe? Well, let's take it one step further here. What if I put this all together and I know the equation of a line, a linear equation, can be gotten by y minus y1 equals m, which is the slope, times x minus x1. What if I plug in the slope here is m is 4, and the point is x1, y1, right? So I have y minus y1, which is 5, equals the slope, which is 4, times x minus the x coordinate, which was 2. Now, if I do some algebra, I've got y minus 5 equals, distribute, 4 times x is 4x, minus 4 times 2 is 8. And now I just add this 5 to both sides. What is my linear equation? I have y equals 4x, negative 8 plus 5 is a negative 3. So that is my tangent line. That should be my line tangent to x squared plus 1 at that point, 2 comma 5. All right, so we're going to take a look if this is indeed true using Desmos. Is this line y equals 4x minus 3, is it tangent to the curve x squared plus 1 at this point, 2 comma 5? We're about to take a look. Okay, so here we are in Desmos, and you can see that the red curve is the function f of x equals x squared plus 1. We just found out analytically that the derivative f prime of x is 2x. So evaluated at the point 2 comma 1, if you plug in the 2, 2 times 2 is 4, so the slope is 4 at that point. And we figured out that the tangent line is gotten by y equals 4x minus 3. So if I leave up this graph here of f of x equals x squared plus 1, and I add in y equals 4x minus 3, look what happens. We get a line perfectly tangent to the point 2 comma 5, which verifies that our slope at that point is indeed 4. So at this particular point in time, an object could be going at 4 miles per hour, 4 meters per second, or what have you. So again, the derivative is a function that tells us the rate of change or speed at any point we might want to plug in. And the last thing we'll investigate here is again looking at our function f of x equals x squared plus 1. We found the derivative f prime of x is 2x. And what if we want to know now, what is the slope at negative 1 comma 2? So if I go to that point, over 1 up 2, I'm right here. So the slope would be the tangent line approximately like that to the line. That would give us the instantaneous speed or rate of change right at that point. So how do we do it? Well, we are going to substitute in our x coordinate here is negative 1. So in our derivative, f prime evaluated at negative 1 is equal to this 2x, but now x becomes negative 1. So 2 times negative 1 is negative 2. So that is our slope m. So the slope or the speed or rate of change, velocity, whatever you want to think about, at this particular moment in time, the slope is negative 2, okay? What if I want to write the equation of the tangent line? Well, we have y minus y1 equals the slope times x minus x1. And if we plug in, we have y minus, the y coordinate here is 2, equals the slope, which is negative 2, times x minus the x coordinate. The x coordinate is negative 1, minus the negative 1 is plus 1. Now we'll do a rewrite. Y minus 2 is equal to distribute. Negative 2 times x is negative 2x. Negative 2 times 1 is minus 2. We'll add the 2 to both sides. And we have y is equal to negative 2x. And the minus 2 plus 2 cancel. So there is your equation of the tangent line. Y is equal to negative 2x. Now, let's see what happens if we graph that, if we add it into Desmos. So let's try it. Let's queue up a second graph here and put in y equals 2x, negative 2x, and bam, there you go. It goes right through my yellow hand-drawn line. That is the tangent line at the point negative 1 comma 2. So there you have it. This is calculus. You're doing differentiation, finding the derivative. I hope this video helped. And remember, just like calculus means a small pebble, this is just one small stone thrown into the pond in your endeavors and learning about calculus. So if it doesn't make sense right now, it really shouldn't. So you're just starting. So thank you very much for watching this video. Thanks for hanging in and hope you learned something new. Have a great day.